These are our three basic steps for a titration. We are going to know the molarity of our titrant. So in this case, we know in our lab, we had 1.0 molar NaOH. We're going to use our data to find the equivalence point volume of NaOH, the amount that I needed to completely react with my analyte. I know how many drops of hydrochloric acid I put in. I just want to think about what is the molarity of my hydrochloric acid, my analyte. So first things first, we need to use our data to find the equivalence point. We started with a bunch of HCl in the flask. At the equivalence point, we will use either the indicator or the pH to know that we have added enough sodium hydroxide to completely react with all of the acid we started with. So at this point, we're going to look at our data and we're going to look for two places. One is where you added one drop and the color stayed pink. So that is our equivalence point number of drops for the indicator. That's the first number that you're going to put in underneath your graph square on your lab, the number of drops according to the indicator. In a minute, we'll figure out how to turn that into a number of actual milliliters. The other way of finding the equivalence point is by looking for that dramatic change in pH. If we had hit it perfectly just on, we would have ended up exactly at 7 because our products are just water, which has a pH of 7, and a neutral salt because the conjugates of a very strong acid and base are really, really weak. You probably had a point at like 4 or 5 and then a point at 9 or 10. That dramatic change, that's the number of drops where you found the equivalence point according to the pH. So let's think about how to do this. In order to do this, we really need to get from drops into milliliters. Then we can actually work in real units. So 1 drop is 0.05 milliliters. So if we think about doing this as a little unit conversion, we would put 0.05 milliliters on the top and 1 drop on the bottom. So our number of drops times 0.05 will give me our number of milliliters. So you have 2 individual numbers of drops, and you need to convert those into milliliters. I am going to use an example number to do that. My example number I'm going to pick is 28 drops. Let's say at 28 drops, I have a pH change, and so I go through a pH of 7. So if I want to get 28 drops into milliliters, I take 28 and I multiply it by 0.05, which gives me that is 1.4 milliliters. So now I know the 2 things I need to do the first step of my 3-step titration problem. Remember, the first step was to get into moles of titrant or millimoles of titrant. So I'll take my 1.4 milliliters, multiply it by the molarity, which is millimoles over milliliters, and that will tell me that I had 1.4 millimoles of sodium hydroxide. That's how much I needed to add to get to the equivalence point to react with all of the acid that I put in my flask. Well, that was step 1, get into moles. Step 2 then is to use my stoichiometry. So now that I have my millimoles of titrant, millimoles of NaOH, I can use my balanced chemical equation to start talking about millimoles of the analyte, HCl. So luckily, this is a balanced chemical equation, and that means that the math is going to be very simple here. 1 millimole of NaOH, you see 1 millimole of NaOH on the bottom, so it'll cancel. 1 millimole of HCl up top. Since this is a 1-to-1 reaction, if I needed 1.4 millimoles to react, it means I had to start with 1.4 millimoles of acid. So now I've used my stoichiometry here, and even if it is a 1-to-1 reaction, you really cannot skip this step because you need to have that step and that muscle memory and the routine of checking your stoichiometry, because one of the most common errors is forgetting when something is not a 1-to-1 reaction. So Now that I have millimoles of my analyte, HCl, I want to find molarity of my analyte. And that means I need a number of milliliters because millimoles over milliliters is big M molarity. So if I had 25 drops of HCl at 0.05 milliliters per drop, I had 1.25 milliliters. You will also have 1.25 milliliters, assuming you started with 25 drops of HCl. So to get big M, I take my millimoles, which I got from the last slide, divided by my milliliters, which I have right here, and I have two significant digits because I'm dealing with 25 drops and 28 drops, so I have 1.1 big M. Really, all titration problems work essentially exactly the same way. They have those three individual steps. Get into millimoles of titrant, use your stoichiometry so you can talk about analyte, and then if you're doing molarity of the analyte, you just take that number of millimoles and divide by the volume of your analyte. So along with not checking your stoichiometry, one of the most common things people do is they switch around numbers. They put titrant volumes where analyte volumes should go, something like that. So I wanted to look at an example real quick. Also, you do need to calculate the percent error. So here is the percent error formula if you've forgotten it. You can pause this and write that down so you can do this for your lab. And of course, you can print out the graph. You should have saved that to a Google Doc so you can print it out. If you're going to make the graph by hand, God, why? But if you're going to make the graph by hand, make very sure it is actually correct. Don't just sketch a random shape. I will check to make sure that the graph is actually correct to your data. So here's an example problem. 43.1 milliliters of 1.3 molar KOH are required to neutralize 50 milliliters of H2SO4. Find the molarity of H2SO4. So what that tells me is that the H2SO4 is my analyte. That's what I'm trying to analyze to find something out about. And that means the potassium hydroxide solution is my titrant. So let's see if we can kind of organize this to help us. So my analyte is the acid, H2SO4. And what do I know about the analyte? Well, I know I want to find the molarity, and I know that it was 50 milliliters of H2SO4. On the titrant side with my potassium hydroxide, I had 1.3 molar solution, and it was 43.1 milliliters to reach the equivalence point, to neutralize it. A neutral pH is 7. That's where the equivalence point is of a strong titration. So step 1 was to get our moles or millimoles of titrant. I have a molarity and a volume. If I multiply those together, I get my millimoles. I've done step 1. Step 2 is to use my stoichiometry. So if I do look at this, this is not a 1-to-1 reaction. This is a 1-to-2 reaction because there are two H's in H2SO4. So each H2SO4 is going to need to find two OH's to react with. If you write out your balanced chemical equation, you'll see that H2SO4 plus KOH makes water, of course, and a salt, and that salt is potassium sulfate, which would need to be K2SO4 so that the charges balance in my products. That means I need 2 potassium hydroxides, and I will end up making 2 waters. So for every 1 H2SO4, I need 2 KOH. And that means that when I use my stoichiometry, I don't have 56 moles of my analyte. I only have 28 millimoles of my analyte. That's step 2. I've found my moles, I've found my stoichiometry, now I just need to get my molarity, step 3. So if I want to get the molarity here, well, remember, I know all this, That's going to be my millimoles over my milliliters. And I know that my volume of analyte, the H2SO4, is 50. So that's 28 divided by 50, or 0.56 molar. All of these problems really follow the same set of steps. So make sure and work on your lab, and we're going to pick this up on Monday with a graph, please, that is correct, either printed or correctly graphed with correct labeled axes. It's much, much easier to print it, but you do you. So have a good night. I'll see you tomorrow.